Thank you for the introduction, and thanks to the organizers for the invitation to present here today. So I'm Daan. I work at Lawrence Berkeley National Lab at the National Energy Research Scientific Computing Center, and specifically the Advanced Technologies Group. So the title of my talk today is stated as Measurement-Driven Quantum Algorithms, and I want to talk about eigensolvers. There's going to be quite some overlap, I believe, with work that was presented in the previous talks and some work yesterday, and also think about how we can use these type of methods to evaluate matrix functions on quantum computers. Before I get started, I want to acknowledge all the wonderful collaborators I've worked with for the stuff I'm hoping to talk to you about today. So if time permits, I'll talk about these three papers that I've listed in the bottom. I'm going to start with the one in green, the ODMD, which stands for Observable Dynamic Mode Decomposition, which is an eigensolver based on signal processing and subspace methods. Next, we'll move on to MODMD, which stands for Multi-Observable Dynamic Mode Decomposition, which was a collaboration with the Yellen group from Harvard. And then finally, if time permits, about this more recent paper on using quantum Krylov type algorithms for matrix function evaluation, which was a collaboration with Will Kirby and Anirban Chowdhury from IBM. So by means of introduction, let me add some high-level thoughts about this NISQ versus fault-tolerant and early fault-tolerant chasm and bridging that gap that this workshop is all about. So I come from it from more of an algorithms developer's point of view. And there's at different levels, there's distinctions between both, but at certain levels there may also be some commonalities. So much of this won't be very new to most of you, but in the NISQ level, the types of operations you optimize for when you optimize your circuit are quite different maybe than for fault-tolerant implementations, where you have C-naughts versus T-gaze optimizations, and the type of algorithms can also be quite different. At the highest level of like designing and thinking about an algorithm, there may be commonalities in terms of like we want to look for algorithms that optimize time to solution, converge fast, give accurate solutions, and so forth. I also really want to shout out this paper for, I think, for which most or all of the co-authors are in the audience, and which was mentioned yesterday, which gives this architectural point of view of bridging this gap and introduces this model in terms of scalability and errors required for scaling from NISQ to early fault-tolerant. So my hope is to maybe give some arguments that what we call in this talk measurement-driven approaches are interesting candidates to look at and explore in this intermediate regime. So what do I mean when I say measurement-driven approaches? It's quite a general term and maybe not that widely used, but it's an umbrella term that I want to give to methods that try to offload some of the computation from the quantum computer to the classical computer by using classical algorithms from signal processing and linear algebra. So the workflow on a high level looks like you run quantum circuits on your quantum computer, you collect your measurement results, and you post-process them. Possibly you repeat it if you need to collect more data. There's some difference with the variational type of approaches like VQE, where I think the key difference is that in this type of class of algorithms, you do not require variational parameters updates, so you avoid this optimization problem that these methods suffer from. And you still have the power of trading off circuit depth for samples. So with that being said, let me talk about a few results that we have in this space for computing eigenenergies and phase estimation type algorithms. So the problem formulation, it's well known. We have some quantum many-body system, for example, FOMOCO, and we want to estimate the ground state energy or low-lying eigenvalues of this system. This boils down to a large-scale eigenvalue problem that we want to solve on the quantum computer. I learned yesterday that there's recent work that maybe some of these problems can be solved on classical computers if you have enough resources and use clever algorithms. So I guess the word is still out of where quantum computers are the most promising, or what the most promising applications are for quantum computers in this space. But it's an exciting field and an exciting topic nonetheless. So we want to think about workflows that use the quantum computer to evaluate some unitary that in some way encodes our Hamiltonian that we want to get the energy estimates for, and then collect the data, and with some post-processing get these estimates out of our workflow. So the textbook case is quantum phase estimation. This is probably quite well known to most or all of you. So we have this quantum circuit, this quantum algorithm, which has this ancilla register and then this repeated controlled unitary applications of our typically time evolution operator. And at the end, if we feed it a good initial state, we read out the corresponding energy on the ancilla register. If you want to reach a certain precision up to some additive error epsilon, the depth of this circuit scales inversely proportionally with this error. In terms of simulation time, this means that it scales inversely proportionally with simulation time if you do time evolution. Which can be quite challenging in near-term devices. So we're interested in seeing if we can come up with different methods that maybe reduce that strict depth requirement a little bit by trading off taking multiple samples to compute your answer. So one idea in this space, which was proposed like probably originally like five-ish years ago, and it's in this class of hybrid quantum phase estimation algorithms, is a method called subspace expansion through real-time evolution. There's these two papers from Parrish and McMahon and from my colleague Katie Klimko from 2022 that proposed and studied this method. And in this method, the idea is you have some initial reference state, you assume that you can do time evolution efficiently on your quantum computer, and you construct some basis of, let's say, n real-time expansion states starting from this initial reference state. So I represent this basis here as this tall, skinny matrix of quantum states. And on the quantum computer, this is a procedure that was mentioned in multiple previous talks. You do some Rayleigh-Ritz procedure to measure the matrix elements of your Hamiltonian in this basis and the inner products, the overlap matrix, or the Gramian matrix. So you do this procedure on a quantum computer, doing some Hadamard-test style circuits. You end up with this eigenvalue problem, this small-scale generalized eigenvalue problem, where you have two matrices. One is the projected Hamiltonian, and one is the overlap matrix. If you do your time evolution exactly, both matrices would be tuplets matrices, so you would only need a linear number of matrix elements potentially. But if you trotterize this time evolution operator, you typically lose this tuplet structure, and the number of different matrix elements you need to measure grows quadratically in the subspace dimension. The key strengths of this type of approach is that numerical evidence shows that they often can converge to ground states in very low-dimensional subspaces, and this also gives a low-dimensional representation of the ground state within the subspace, which would be the orange Ritz vector. The challenges with this type of methods are that these eigenvalue problems, they're typically ill-conditioned. The bases are non-orthogonal. There's linear dependencies. There's ways of regularizing this through SVD and truncation approaches, but it's quite a heuristic approach with its challenges. And then a second challenge, or another challenge with this, is the measurement cost for each individual matrix element, which, if you want to reduce the error, you need to by some factor, you need to take the square of that factor more samples.
Yeah. So, question. So why is this method only require minimum conditions on precise error to convert to the ground state manifold? So I think since you only do the Hamiltonian simulation here, you at least need some overlap.
Yeah, I mean, minimal conditions, I mean, the overlap can be quite small. You need a non-zero overlap. It shouldn't vanish, but these methods, at least in our numerical evidence and numerical studies, they still converge with relatively small overlaps on the order of like maybe below 50%, maybe 10 to 20% of overlap.
Okay, but I guess so you cannot deal with like exponentially small overlap.
No, definitely not exponentially small.
Yeah, sure.
Is it understood how the measurement cost depends on the condition number?
I would say the condition number mostly depends on the like it grows with the dimension of the subspace. If your measurement like if your measurement budget is quite small, there will be a lot of error on your matrix elements, and this may deteriorate your condition number further. Yeah, but I'm not sure if there is a very clear relation between them.
Okay, so like the epsilon in the bottom row, is that the accuracy for
a given matrix element? Yeah.
Yeah. Okay, because I think I'd be interested to understand, given an accuracy, like a target accuracy on the reported ground state energy.
Yeah.
What is the dependence of measurement costs on that and condition?
That would be a very interesting question.
So I do think for this question, one thing I know is this method cannot achieve the Heisenberg limited scale.
Right. Yeah.
So because you use the uniform time grid, and there is a lower bound thing that the best you can achieve is 1 over epsilon to the power 1.5.
Yeah.
There are some lower bound results. Yeah.
So one adaptation to this method is to go to the unitary version of that, where the only difference is instead of projecting the Hamiltonian, you project the time evolution operator on this subspace. This means that you reduce the number of different matrix elements from n squared to n, because both on the left-hand side and the right-hand side of your generalized eigenvalue problem, you use the same data. It's just shifted by along the diagonal. And I'll denote this data that we measure as this S sub k vector. It's the time series data, and that leads into my next slide. There's a separate point of view of these hybrid quantum phase estimation type methods that take the signal processing type of view, where we have these time-evolved states from some reference state. If we fill out the spectral decomposition of our Hamiltonian into this equation, we can write this as some linear combination of some coefficients, which are the overlap with the individual eigenstates, and some complex rotating phases with the states being the eigenstates. So these overlaps, they reduce to something that looks like this, where we have these weights determined by the overlap of the initial state, and then some complex phases. We can think of this as some sum of sinusoids, where we can do signal processing methods to analyze the data if we collect this from the quantum computer. So these type of methods on a very high level, they filter the dominant modes from this time series data to get an estimate of what the dominant oscillations are in the signal that's collected. There's papers out there that show that these methods are quite robust in terms of additive noise. They don't require solving this ill-conditioned eigenvalue problem. It's less clear how to get this lower dimensional representation from the ground state from these methods, maybe. And the initial overlap with the ground state energy, typically in our numerics, needs to be a little higher compared to maybe these eigenvalue problems. And it's in this spirit that I want to start talking about this observable dynamic mode decomposition, which is the algorithm that we've looked at in our work. So what does it do? It starts from this same time series data, this sum of sinusoids data, and we measure it at different time points, look like this time series of what we call observables. And then we aim to use this machinery from the dynamic mode decomposition literature, which is a model reduction method that is widely used in fluid dynamics to analyze the data set. In this DMD approach, it typically is for some complex nonlinear system and how it evolves in time. So we have some system that evolves by some nonlinear mapping F in state space, and then DMD uses some embedding operator to track how what they're calling an observable evaluates an observable space, and it uses these snapshots of observables of the system to create a reduced order model of the underlying system dynamics of the nonlinear system. In our case, the system is not nonlinear. It's a very large, high-dimensional linear system. These embedding methods, they're maybe in many ways less accessible because we have the measurement problem. So what we decided to do here is to go with a time-delayed embedding. So we start from our time series data, and we kind of group it in buckets, overlying buckets that embed it in feature vectors of some dimension d. These are our snapshots of our observables that we collect in this matrix with this structure, and then we use the DMD approach to compute a reduced order representation of this based on these snapshots. We do this by splitting this matrix in the first k columns and the last k columns, and then solving this least squares problem for some system matrix A, which is our reduced order model for the unitary dynamics that we're trying to capture in this model. So we end up with our matrix A, which an exact arithmetic would have companion structure, and then we diagonalize it classically and extract our energy estimates from this small-scale diagonalization problem. So we, in our paper, we tested this on a few models. I'm showing here the data for a 1D Heisenberg model on 12 sites, and we compared ODMD here in blue with an alternative signal processing and these two subspace methods with different measurement costs, and we showed the convergence to the ground state energy in terms of total simulation time. And we see that it's competitive with alternative approaches, and it can mildly outperform some of these other methods. We do attribute this convergence behavior to the fact that we can think about ODMD as from two sides, from two perspectives, both as a signal processing method. It's isomorphic to matrix pencil methods such as Esprit, and we can also see it as a quantum subspace method. We can think of it as a two-sided Krylov method on the original Hilbert space, or a functional Krylov method of the Koopman operator.
Daan,
Yes.
What does simulation time mean there?
It's the Hamiltonian simulation time that you need to run e to the IHT. Yeah.
Circuit cost.
Yeah, it's our proxy for circuit cost.
Did you check that on like more complicated chaotic Hamiltonians?
We've done these lattice models and some simple molecules in the paper, like lithium hydride, I believe. But it would be interesting to study more systems, yeah.
So these collected data, or no, actually that slide was better. You go back.
Sorry?
You go back to the Hadamard-test.
Here.
So those are the circuits that you're running, right, in order to collect the observable values?
Right, yeah.
So when I think of those, I immediately analogize it to robust phase estimation, Q-cells type work, right? So can you give some intuition as to how is the simulation time scaling compared to those methods, right, those RPE-based methods, the K values present, that seems to be the most direct apples-to-apples comparison, if I'm understanding correctly.
Yeah, here this orange data, the signal processing method, is based on an implementation of Q-cells. So the simulation times that we're seeing is comparable.
And can you also speak as to both the asymptotics and also not just total simulation time, but also the maximum circuit, like the maximum K present?
I will say a little bit more about that in the next part about where I'll talk about MODMD. It's based on a paper of Seon on the noisy super resolution type methods.
Okay, so I should be thinking about it as a more explicit way to filter out those higher frequency components.
Yeah, yeah.
Thank you.
So what's the initial state you use for this simulation?
I think we use the state with, I forgot the exact overlap with the ground state, but like on the order, maybe, I think it was between 10 and 50% of overlap with the ground state, yeah.
Yeah, so, a quick question. So, when you say that the signal processing method is similar to the S-split, but you also say it's similar to Q cells. But S-split and Q cells are completely different.
I know. I'm saying ODMD is similar to S-split. The orange data we collected here was using some version of Q cells. Okay. So going into this extension to MODMD, here the high-level question you ask yourself is, if we collect this data from the quantum computer and you do these measurements using the Hadamard-test, you throw away a lot of data at the end of your circuit. You only measure this one ancilla, but you don't do anything useful with the system qubits. Is there a way that we can adapt the circuit and maybe measure all the qubits and extract more information from each individual circuit run? And maybe instead of capturing this single time series, we have this what we call the multiple observable signal vector out of the one circuit. And in our work, we show that you can do so by using classical shadows and adding at the end of your circuit some random unitary that has a pretty modest circuit depth. So this doesn't cost too much in terms of circuit depth if you want to do this. And on the quantum side, it means that you start off in a very similar fashion than before. You run your shallow shadow circuit, you collect your data set, and then from this data set, it gives you the ability to predict many properties of the initial state that you've prepared. In our case, we're looking at properties that look like this, where we, instead of just looking at the overlap with the k-power view, we insert some random observables into this. And what can these observables be? They can be, there's a lot of flexibility in this. They can be 1 qubit, but they can also be pretty high weight observables. And this allows us to collect this multi-observable signal S, boldface S sub k, at a cost which only depends logarithmically on the number of observables. So this is quite efficient, this procedure, and it matches quite well with the type of data we're interested in collecting. So that's the circuits we run on the quantum side. The classical post-processing side based on this data set is quite similar to ODMD. So instead of having this single time series, we now have this vector of time series, and we can represent this as these L different least squares problems, which we solve as some block matrix version of it, a much bigger system matrix, but still not exponentially big in the system dimension. So this makes MODMD a block crowd of subspace methods. And if your overlap is large enough, given to the fact that it's similar to an Esprit type method, based on this result from 2024, it can be shown that the circuit depth can be somewhat smaller than for phase estimation in principle.
Just a question on these SKs. Could you explain why those classical shadows samples are giving you these overlap estimates instead of some expectation values, say of like the time evolved state?
You mean why? Well, we can write it such that we get this data out of it.
Oh, you can like recombine.
Yes. Yeah. Yeah.
Is that easy to see?
Maybe not directly, no. But the details are in the paper.
We need to have some sort of commutativity of OIs we use.
There are restrictions on OI. Yes. I think these are typically Cliffords, but I don't think they have to commute with you. So we. Oh, sorry.
May I ask you, is there any constraint on those observable? Because we kind of know if you want to do this kind of high weight operator, the classical shadow will be like exponentially inefficient.
What do you mean with a hybrid operator?
I mean, like if the constraint on the operator O.
Mm-hmm.
Because if you want to use classical shadow to estimate like this kind of high weight poly operator,
right,
it's exponentially inefficient.
Yeah, I think in our numerics we typically use quite like low weight operators, low weight polys.
Does the weight of the operator like change the performance of the algorithm, or?
I'm not too sure about that actually. I think that would be interesting to study.
Yeah. So one thing I'm curious about is what we want to set the cost to be more in L. I think in the end you will at the most use L equals to poly n, right? So therefore, for me, L or log L are almost the same.
Sorry, I didn't quite catch the.
Yeah. So for examples, if the goal is only to avoid the exponential cost, then I guess you will always choose this L to be polynomially in the number of qubits.
The number of observables.
Yeah.
Yeah. We choose is typically quite small.
Right. So even you don't use classical shadow, meaning that your cost will be linear in L. It's still okay.
It's not. It's a logarithmic improvement over a relatively small number. Yes. Yeah. So we tested this again on a spin chain model, for example, with 15 sites, and here we compare MODMD with our original ODMD, where we just have the original time series, and here we use 7 different observables, and we look at the convergence of the first 4 eigenenergies. We see that there's not a huge difference in terms of the convergence to the ground state energy. ODMD captures that quite nicely, but if we look at the low-lying excited states, we see that this block subspace can capture these. It's similar cost as the ground state energy. So if you're interested in excited states, this can offer quite some benefits potentially. In the next comparison, we compared this MODMD approach to a method called QMax and UVQP, which is a subspace method. We gave both of them the 7 different observables that we used with MODMD. And then we again looked at the first 4 eigenenergies. And on the y-axis here, we plot the enhancement, which is the reduction in error that MODMD gives over these comparable methods, and we see that we can outperform them with maybe 1 to 2, in some cases 3 orders of magnitude of precision at longer simulation times.
Sort of a conceptual question. Does MODMD look for correlations between the signals that you find in your different observables?
Well, we solve this matrix, so it does take into account the correlations between the observables. Yeah.
Okay, and that's how you get a higher accuracy out of something like a heterodyne measurement.
Yes. Yeah.
And are those simulations like assuming like perfect estimates of the?
We add some Gaussian noise to mimic the shot noise effect, but outside of that, I think the time illusion is using Trotter, but it's all done exactly in a way.
Okay. also on the system register, is there some, how do you incorporate the classical shadows, using the classical shadows samples?
I think we just add noise at the very end after the simulation.
And any intuition for why it helps on the excited state estimates?
Because I think it's because of this block subspace feature, where instead of just having a single reference state which converges to the ground state but takes a long time to converge to the energy, I think these extra correlations can capture also the higher excited states.
And what's the intuition behind why it doesn't help the ground state estimate very much?
That's a great question, actually.
So one potential thought is your observable is an operator that knocks you out of your ground state.
Right.
So
Yep.
you pick up a lot of the other things
Yep.
that are going on, but the inner product with the ground state could be small.
That's fair. Yep. Okay, I think I still have some time left for the second part of my talk, where I want to talk about this third paper where we used a very similar framework to not to do ground state estimation, but to evaluate matrix functions. So here, the problem setting is as follows. We assume we can query some unitary, and we want to compute properties of a function of this unitary, typically these type of overlaps. This has applications to, for example, Gibbs sampling, linear systems, or more general Green's functions, and a known quantum algorithm that solves this problem is quantum eigenvalue transformation of unitaries, or CATU. This has a lot of advantages. It coherently prepares this state at the end of your register. It can measure basically anything you want from that. One key characteristic of this method is that these phases, these phase factors, they uniquely determine the function that you're implementing. So if you want to evaluate it for a different function, you need to update your circuit and run it again. So in this paper, we propose a method that we're calling quantum Szego quadrature. Szego quadrature is an optimal quadrature rule on the unit circle. So it's a classical quadrature method. What is a quadrature rule? It's a way of writing this functional that we're interested in as some linear combination of weights and function evaluations in some nodes lambda k, and we denote this rule as this functional of f, r of f, and ideally you would like that this d is much smaller than the dimension of your operator. What is maybe some intuition behind why you want to write this in such a way is if we look again at the spectral decomposition of our unitary, and we plug in this form, we get something that looks like this. And then if we want to compute these type of overlaps that we're interested in, we get something that looks remarkably similar to the quadrature rule, but it has large n terms in the expansion. So this is the actual integral functional that exactly corresponds to the quantity we're interested in.
Can you just remind me what the difference between d and n is?
So n is the dimension of our U. It's the Hilbert space dimension. And d, we ideally want much smaller than U. We want some low dimensional representation of this quantity. Szego quadrature is a way of computing these quadrature rules such that they exactly interpolate Leroy polynomials of degree d minus 1. And our QSQ method approximate this integral functional using this Szego quadrature rule R of f with nodes lambda k and weights that we compute using something we call the quantumizer metric Arnoldi method. So how does it work? It starts off very similar to what we've seen before. So we have our basis states. We project our unitary operator into that basis. We get our small scale projected unitary and our overlap matrix, which we call our Gram matrix. We use that to classically do Gram-Schmidt orthogonalization of the subspace. So these capture all the inner products between the states, and we can use these to actually try to orthogonalize the basis in classical post-processing. In exact arithmetic, this would give a projected unitary that is upper Hessenberg, but it's not unitary. It can be made unitary just by rescaling the final column of this U, which is U hat. And then if we diagonalize this U hat, the Ritz values or the eigenvalues of the small matrix gives you the quadrature nodes, and the first elements of the eigenvectors give you the quadrature weights. So this is all exactly. In the presence of noise, we propose some ways to regularize this problem. So we do two things. We do Tikhonov regularization on S to mitigate the L conditioning and make sure that S is positive definite. And then in this step, we use the SVD. Instead of just rescaling this final column, we use the SVD to find the closest unitary matrix to the matrix that we actually compute. In our experiments, we show, and I'll show some data in the next slide, we show that this converges quite quickly as well. A key strength of this is that we only need to collect this data once, this omegas and lambdas, and we can evaluate it for any function f. So if we want to change our function, we can use the same data. The error may be different because it's less well approximated by a Leroy polynomial of degree d, but we can use the same data set to evaluate it in for different functions. A main difference with CAT-U is that it doesn't give you coherent access to this state, but it still allows us to compute these scalar properties that we're interested in. So here are some numerics, again, for a lattice model. So we look at a 2D Heisenberg model on 12 sides, and I show 3 different plots. On the left, it's just a sanity check. So we show the convergence for a random Leroy polynomial of increasing degree, and we show that exactly at trial of dimension d+1, this drops to machine precision, and the QSQ algorithm recovers the requested function exactly, which is what the theory said it would do. And the second example, we looked at some Gibbs state measurement where we used the unitary to approximate the Gibbs state and compute this overlap, and we see that it converges for different values of beta in like relatively limited low dimensional Krylov subspaces. And the final example is some Green's function example where over this significantly large range of omega, we are able to capture a quite faithful representation of the actual Green's function. I think this is in a 30-dimensional Krylov subspace. So these are some examples of what you can do with this method. We haven't fully explored the full breadth of applications in much depth, but I think it's quite an interesting algorithm to investigate further. Yeah.
So let me make sure I follow what you're doing. These are all functions of the Hamiltonian.
Yes. Yeah.
So the only thing that this requires is measurement of the Hamiltonian in your subspace basis.
We measure the unitary, and then we map that to the
unitary
Hamiltonian.
is also a function of the
Right. Yeah.
Hamiltonian. Could
Yes.
you measure the Hamiltonian?
Well, that would require more measurements.
Why?
Because of this, like if you measure the Hamiltonian, you get this non-tuplet structure, and here we only need this linear number of measurements.
I see. Okay, but like that's a question of number of measurements. Like conceptually, it's the same thing.
Yes. Yeah.
Okay. So you could do this classically as well.
Well, this is the post-processing is all done
No,
classically.
but like you could make this an entirely classical
Right, yeah.
Why do people not do this classic?
Well, people
You
use...
this, the Lanchos, right?
Well, like this is quantum isometric. Isometric Arnoldi is a classical algorithm that uses the nodes and quadratures for Szego quadrature rules. Yeah. Oh, okay. I thought I was running out of time, so I'll end a bit early. My talk tried to introduce the concept of these measurement-driven approaches, which are optimization-free approaches for energy estimation. We talked about ODMD, MODMD, and QSQ for matrix function evaluations. We use the toolkit from classical algorithms based on subspace and signal processing IDs. And these are, in my opinion, quite powerful tools to complement and support a quantum computer. And MODMD in particular combines both subspace IDs with signal processing IDs and randomized algorithms to improve the spectral estimation for specifically for excited states. I'll add the three references that I talked about here. And before I fully end, I want to give a quick shout out to these programs we're running at NISQ. If any one of you is interested in getting access to quantum computers or classical supercomputers, we currently have 3 calls for proposals open to apply for access to devices from IBM, Carrera, and our Perlmutter supercomputer. With that, I'd like to thank you for your attention.